Hearing none, let's go with a great speaker tonight. Steve Murray is an SDAA member. We've had him in our program meetings, got a PhD in engineering and a great career. And he's even been a visiting professor at the University of San Diego. He's done multiple talks for us, as I've said, and I particularly remember one that he did about 4 or 5 years ago, talking about his visit to the great telescopes down in Chile at the Atacama Desert at multiple sites. It was quite interesting and revealing. We learned a lot about the sites, the experience, and the telescopes themselves. And Steve has been very gracious at filling in kind of at the last minute to put this talk together, which is all about new techniques for detecting life in the solar system. So without any further ado, let me turn it over to you, Steve, and I'll try to stop sharing my screen.
All set?
All set.
Everybody can hear me, okay. Yeah, thanks for inviting me. This is actually a fun topic to put together. I've been around enough that I guess most people know how the Solar System Ambassador program works. Got a lot of these materials from NASA, but more than some other topics I've done, I had to go far afield and do a little searching on my own. So any mistakes tonight, any errors are almost uniquely mine. I've always been interested in it, and I grew up, everybody thought we were going to be shaking hands with Martians. But NASA got into this game in the late 50s and established an official exobiology program in 1960. So they've been around for a while. It's headquartered up at Ames Research Center now. It's an astrobiology effort, not exobiology anymore. And I think the Europeans have an equivalent program. I'm going to talk a little about technosignatures tonight, which wanders into SETI territory. NASA's been interested in that too. They had a brief program in '71, but it didn't last long. And they tried to start it up again in 1992, and Congress debudgeted it almost a year later. So they've never wandered into SETI searches. And today, the two SETI searches that are major ones that are underway are funded privately or through various investment and other external investors. But the dream stayed alive. In 1976, Viking missions had 3 biology experiments aboard our first attempt at landing on the red planet. And those results are still being debated today, what they found. And pretty much several times, I guess everything here you see is in the 70s. If we had a chance of leaving a breadcrumb or saying hi to folks on other parts of the galaxy, NASA took advantage of it. Now, quick definition here, because as I said, the name has changed. Astrobiology incorporates life everywhere and at all times, even life that isn't around anymore. And it includes both biology and technology. Exobiology was the earlier term, strictly life found on places other than Earth. It's turned out, ironically, that the effort to search for interstellar life has caused us to relook at how we view our own planet, its geology, its evolution, and its biology. Xenobiology is kind of a funny term. My reading showed that it was invented by Robert Heinlein, which gives it kind of a science fiction flavor back when aliens could be based on silicon. But that's what the term means, life based on foreign chemistry. And it is, in fact, a real field. These are chemistry experiments, chemistry modeling, but you can form complex molecules out of silicon and sulfur. There are solvents to facilitate chemical reactions other than water. To my knowledge, though, it's not really considered part of astrobiology today, only because they've got bigger issues to explore. Okay, this is a 1998 astrobiology roadmap. I'm told it hasn't been changed in any substantive way. You can read uh, uh, fairly easily here. I did want to point out, though, it says explore habitable or formerly habitable environments. That's the first point tonight. If we found evidence of past life, that would be just as profound a discovery for science as finding active life today. And as I've introduced earlier, the big emphasis here is putting the emergence and evolution of life here on Earth into a larger context in the galaxy, asking old questions in new ways. So a surprising emphasis is to start here and then branch out, searching for life elsewhere. Okay, there's two ways that they look at how life got going here and how we got where we are. They both kind of lead to the same end with a different process. The first is abiogenesis, and we're trying to figure out where did the transition occur between the basic molecules that were available on the ancient Earth. When did those transition into biomolecules? That involves minerals from rocks, water that was here at the time, didn't have to be oxygen. I've listed the three primary biomolecules here in the lower left. You can see same thing for all of them. Carbon, hydrogen, oxygen taken from somewhere other than the atmosphere. And I think that's it. The P here is a phosphate and the R is just a radical. One of the things about organic molecules and why we think carbon is the basis for organic life is it bonds well. There are strong bonds with it and lots of other elements, lots of other molecules. Lipids give structure to biological organisms. Amino acids are the ones that make proteins. Nucleic acids, and there are plenty of them, are involved in RNA and DNA. Okay, how do we go from rocks and water to those? The biggest stab was taken right to the heart of the issue in 1953. If you remember from high school biology, the Miller-Urey experiment. These researchers took water, methane, ammonia, and hydrogen, all molecules presumed to be on ancient Earth, pre-oxygen. This is back at the dawn of time. Put them in a container, added an electrical charge, simulating lightning that existed then as well. They let it sit for like 5 days, came back, and they had several amino acids formed in less than a week. That was the first stake in the astrobiology sands, in that it showed you could go from rock, water, mineral molecules to a form of biomolecule, and fairly quickly. That fell into disrepute some years later. Other scientists found there were things in the early planet's surface and atmosphere that would have prevented the formation of amino acids. Making this not too dramatic a story, in the 80s, they revised what existed in the ancient Earth surface to say, well, there are other things that would have prevented the things that prevented the amino acids. So they put the whole collection in a jar and repeated the experiment after, I think Urey died first, Stanley Miller died in 2007. His last career was at UC San Diego, and his student ran it in 2007 and came up with even more amino acids. So bottom line, that was a seminal experiment that showed how abiogenesis could occur on the Earth. There doesn't seem to be a big controversy about the process of abiogenesis as the origin of at least the materials, the biomolecules I showed here. It stops short, of course, all right, how do you take those and turn them into living, reproducing life forms? But it was an important bridge to start. The other theory is life just came to us from someplace else. It's various degrees of ready-made. Some of you might remember a picture of this from 1996. This was a meteorite that had been recovered from Antarctica. It had come from Mars. Pieces of Mars have landed around the world. That's itself not a big surprise. But when they studied it, they found what looked like this little segmented worm. And I remember Dan Golden, the NASA director at the time, holding this big, profound, serious news conference to say we found it. And as you'll see with a lot of this science, it didn't take long before people came up with alternate explanations and tamped those expectations down. That's not really considered that exciting anymore. But if you're looking for an example of what panspermia means, that's it. Came from another body, landed on Earth, and spread life that way. A better example, more meaningful example, is the Murchison meteorite. Landed in Australia near the town of Murchison in 1969. One of the good news for science, one of the pieces of good news for science here was that people saw it fall, so they got on it quickly. They examined it, found it to be 7 million years old, and inside were amino acids, including many of the ones that the Miller-Urey experiment had created. And what's significant about this from an astrobiology perspective is that the kinds of contaminants you would expect from a meteorite that we've recovered after it's been buried for centuries that might have contaminated with Earth materials didn't exist. It was a pristine interior, and it still had amino acids. So that's probably a better way of looking at panspermia. And most bodies in the solar system, in fact, asteroids, comets, the interstellar object Oumuamua, all have organic molecules that could do much the same thing. It's not a big surprise to have those basic materials. What varies is how they get here and what happens to them after they're here. But panspermia is just another method of providing biomolecules. It doesn't get any closer. It would have if the NASA meteorite, the Mars meteorite had panned out. It doesn't get any closer to showing how that bridges from biomolecules to living things. It just shows how things can get started. And of course, if you know that, you get some idea of where it could have started in similar conditions on other worlds. Today, of course, you find life pretty much everywhere. Extremophiles exist around the world in some of the strangest environments. And the little calendar I put in the lower right shows that it started pretty quick. First oceans formed 4 billion years ago. Some unconfirmed evidence think even 0.2 billion years later, you might have had microorganisms. A more reliable measure is 3.5, which is still a remarkably short period of time. Earth forming to first direct evidence of biomolecules, that's 1 billion years. That's less than a quarter of the lifespan of Earth. What I have up in the right corner is the kind of microorganism they're talking about. These are stromatolites. I think they're found elsewhere, but the biggest population is off of Western Australia. These are the oldest samples of microorganisms, and these were produced by cyanobacteria that left a biofilm that embedded sand into it and created these fossil-like structures as records of there having been. It's the bacterial or microorganism version of coral, where polyps leave a shell after they die. The coral is a remnant of the polyps that live there. This is kind of the same thing, much earlier, pre-oxygen. In fact, these kinds of bacteria where you gave off oxygen as a byproduct, as a waste product, and led to the transition of oxygen on Earth and then the evolution of oxygen metabolizing organisms. But these other pictures show some things which I may have shown before in other presentations. Up in the middle, we've got black smokers, 6,000 feet down, 750-degree water. These are geothermal vents below the ocean. And it sounds like a horrible environment, no sunlight down there. And yet we found tube worms and a species of crustacean, like a little tiny shrimp, that live in those conditions. The acidic pools in Yellowstone contain bacteria. Bottom left is Atacama Desert, where they found life in deserts with no recorded rainfall for over 3 million years. So life is pretty hardy and life started pretty soon. So some kind of transition happened early on, regardless of whether you buy the panspermia or the abiogenesis explanations. Okay, so if it's here, can these kinds of things happen anywhere else? Okay, this is the first big topic, is we're looking for biosignatures, indications of biological life. Microorganisms have been here a lot longer than sentient beings on Earth. So they represent a bigger span on our planet. They probably represent a bigger span of life on any planet that might harbor them elsewhere. But there's some qualifiers here that can be sobering. We're not looking for life with a biosignature. We're not looking for life itself. We're looking for an interaction between life and its environment. What did it consume? What did it transform? What did it leave? And then the most strict one of all, no single biosignature clearly demonstrates life. We've had some exciting news the last year. I'll bring up some of those. But if you don't look at them in the context of the materials that are around them, what they're transforming, what conditions they are operating in, then you really don't have anything that you can put confidence in. And for that reason, is my big spoiler alert, as of tonight, there are no plausible biosignatures. There are no plausible technosignatures. I'll get more to those later. But the science is active, the science is evolving, and the science is pretty exciting because, again, it puts Earth forms of life into a broader context. And they're coming up with some interesting tools to tackle this issue. Certainly hasn't dampened anybody's enthusiasm in the field for looking. Okay, I'm going to start real quick with a survey around the solar system because this is the easiest system for us to explore. These are the easiest things to see with telescopes. We have an energy source, our sun, which we understand fairly well, certainly better than other stars. We can send probes to these worlds and orbit and land on some of them. So it's sobering to think that with all the resources I'm about to describe, we're still not sure what's there. But this is the best opportunity we have to find some kind of life, present or past. And so this is where I'm going to start reviewing what we've been up to. As I say, requirements for life here in the solar system are an energy source to allow metabolism, liquid water to allow and support chemical reactions, and a carbon-based chemistry. Again, carbon molecules are reasonably stable, in fact, very stable. They make strong bonds with a lot of different elements and compounds. I mentioned the alternatives that xenobiology offers, but nobody's looking seriously at that now. Okay, we'll get right into Venus here. High pressure, 92 bars, incredible pressure at the surface. 470 degrees Celsius at the surface. Nobody's looking at that as a source of life. Excuse me. But last September of 2020, some scientists reported they had found phosphine gas at 180,000 feet up in the Venusian atmosphere. The temperatures there are actually fairly mild. The pressure is much milder. And we have biosphere here on Earth that involve bacteria circulating for most, or some people say all, of their life cycles. So phosphine is produced by the breakdown of organic matter. It got a lot of press, got a lot of attention. Have we found life in the Venusian atmosphere? Well, they got those data from a study with the Maxwell telescope in Hawaii. And MIT came back later and said, no, what you've discovered, I think, is sulfur dioxide, much higher in the atmosphere, that gave a similar signature. The team went back and looked at the data from ALMA telescope array in Chile. Said, nope, there's phosphine there. There's just a lot less of it. Okay, so they modified their original claim, didn't give it up. More recently, I can't remember the institution, someone ran a computer model, and this will come up later in the general difficulties with biosignatures, and said, even if there were phosphine gas there indicating metabolism, there's not enough water vapor. That's a rate limiting compound. There's not enough water in the atmosphere to support life producing that much phosphine. So they found an indirect way of saying that this was not a life form. Most recently, this might be a couple of weeks ago, I think Cornell University attributed it to volcanic action. That's where the phosphine's coming from. So already you're seeing a problem with a very dedicated exploration, very dedicated attempt to find biosignatures. It's a single biosignature. Hadn't really looked at the context. There are limiting factors in the context where it was found. All of them serve to mute the conclusion that this was life. This is not a dead issue, but it's much more measured now in the claims that are made. Now, hopefully we'll get more data on that, if not by other means, certainly by the 3 probes that have been funded to go to Venus in the next 10 years. I think Dr. Smrekar mentioned Veritas and Da Vinci. ESA has got EnVision. All of them have spectrometers capable of analyzing, among other things, the Venusian atmosphere. Da Vinci's going to send a probe down and sample the atmosphere from top to bottom. So, have to wait a decade, but hopefully we'll get some closure on that. Similar issue existed on Mars. A few years ago, Curiosity had found samples of methane. It was transient, it was a small amount, after it had drilled a laser hole, which would seem to fairly localize it. The Mars Reconnaissance Orbiter had been finding methane across large swaths of Mars. Now, that's a biosignature as well, but keep in mind, here we go again, a single biosignature. They still haven't been able to pin down if this is something produced by life or the alternate explanation produced by an interaction of water, rock, and sun. It's not a dead issue. People still talk all excitedly about it, but you've got the same difficulty of trying to claim one thing or another on the basis of small levels of evidence. And this is, all the probes we have on Mars, it's about as good as it gets. Okay, we've got 2 major, not the only, but 2 major probes, explorers on Mars right now. Curiosity, almost a decade. Perseverance, I think just over a year. They look the same, they use a lot of the same parts, they have different software, some different sensors, and different missions. Curiosity was supposed to find if life was possible. Were there conditions on Mars that would lend themselves to the formation of life by any means? And they did. They found water. They found clays and geology that indicated past surface water. Perseverance is there to find if there was life at any time. It's a more direct search. Okay, can we actually find something that we, like the meteorite example earlier, that shows there was life? Notice that, but either one of these is stated in the present tense. If we find existing life, that's a wonderful thing, but we'll be happy if we can just find definitive evidence of past life. Now, for that reason, the Perseverance is scheduled to make a wide surface search across the planet. This is an old projected path from Jezero Crater. I don't know if it's still valid, but the idea is to search along the surface and to cover a lot of lateral ground. This is the Rosalind Franklin rover. This is the European Space Agency's mission, used to call it ExoMars. It was supposed to go at the same time as the wave that was just sent with United Arab Emirates and China and Perseverance. They had problems with their deployment chutes. They decided to wait a cycle. It's going to go in 2022, but then it'll join in 2023 all the other probes that are there now. Europeans produced the rover. The Russians produced the lander, which will also act as a base station. The Europeans have taken a different approach. I talked to the senior scientist before this thing got canceled. I was kind of afraid to call afterward, but he explained in detail why they think that the surface is not hospitable even to past life, that it's the radiation is enough without an atmosphere to sterilize the surface and to break down compounds that might otherwise be clear evidence of past life. Obviously, NASA doesn't feel the same way. So the European rover is going to use a drill to get down where things are better preserved and draw its samples that way. Won't cover a lot of ground. I'm not even sure if it'll roam after it does this kind of a search. Both Perseverance and ExoMars are going to be doing a lot of the chemical analyses, biological analyses on board the rovers. But as I'm sure everybody knows by now, part of the reason for that wide lateral search on Perseverance is it's going to collect samples along its route and put them in a container and get them back to Earth. That's going to launch about 2026. Totally separate mission. Design's not even totally complete. And it's a very complex mission. They're going to send a craft into orbit. The lander you see here will come down, I think 2028. We'll collect, probably Perseverance going to this site, will collect that sample container. It'll launch and rendezvous with the orbiter in 2029 and get back to Earth with it by 2031. Now, there's some issues with this. Last year, they recommended a 2-year delay in that timeline. I don't know if that's funding or technology readiness. I think it's the latter. But an issue came up about 2-3 months ago that's relevant in this context. Where do you want to take the samples once you get them? This is bringing alien material back to Earth. Exactly what are you going to do with it? And at that meeting, some of the astrobiologists say, oh, well, of course, we're going to bring it back to Earth and we'll give test tubes to different labs around in different nations, and we'll all study this in great detail, which is an ideal way to resolve the issue of what's on the surface. There was an equally large body of astrobiologists that said, the heck you will. This is way too dangerous. We don't know what we don't know. Let's have that rendezvous with the Lunar Gateway, which is a space station that will be orbiting, presumably orbiting the moon by then, as a support for crewed landings on the surface. Saying take it to that kind of a location and let them examine these things in orbit. So that hasn't been resolved, but it's a very serious science question, at least for the kinds of explorations, biological explorations we're going to do here in the solar system. Some of you might remember Apollo 11 and the moon. We didn't know that some kind of dangerous biology might exist on the lunar surface. And this was the first time we ever tried to bring materials back from another world. And we quarantined the materials, handled them very carefully. We even quarantined the crew because we didn't know. Now, in retrospect, that may sound a little foolish, but there was nothing to guide us and nothing to disprove it. So what we're contending now with Mars and the Mars sample return is a serious issue. Something that is part of my far afield stretch that I caught wind of the other day, as if COVID itself weren't bad enough. This is a study put out in March 26th of material gathered right here on Earth. They used a robot to go down 14,000 feet in the Pacific, recover sediment. They took the samples back, cultured the bacteria that were there, then put them in samples of mouse cells and human cells. Now, the human immune system, the mammalian immune system, is designed to do one thing, and that's to recognize foreign matter. And it doesn't always react the right way. Sometimes it overreacts, but it reacts. It's supposed to anyway. It rejects some transplant tissue, which it overcompensates for. You remember early in the COVID pandemic, a lot of deaths were attributed to a cytokine explosion, which is a messenger for the immune system that just overreacted. But the point is that at least it reacted. In this case, these cells, which is different than injecting them into animals, admittedly, but they seem to stand by their results. Only 20% of these bacteria from our own planet were recognized by the cells. The other 80% they were just fine with. So I brought this little study up just to emphasize how ignorant we are about the range of things we might encounter. So will the Mars sample return occur? Of course, I'm sure it will. How we handle it maybe still needs some elaboration. NASA has a planetary protection office. They're very particular about what we send to other worlds. They're particular what we bring back, but they're not operating from the same knowledge base, obviously. Okay, those are the two planets that I maintain we're still looking for life, present or past. I wouldn't give up on Venus. I always like showing this slide though, because again, water is necessary for life, and look how it's distributed among solar system moons. Everybody I ask seems to think that the Earth has the most water because it's a fairly big rocky planet and it's all over the surface. But we're actually arid compared to a lot of the moons. Now the trick here is that water liquid? Can it facilitate chemical reactions? And the answer is, if you just look at these moons, no, because it's all frozen on the surface. These bodies are far away from the sun. There's not enough energy to keep the water that we see anyway in a liquid state. But there's more to it than that. Look, these three are considered potential targets. Well, they are targets for potential biological life in the solar system. And that's because there are methods to give enough energy to these worlds to keep water in a liquid state. That has to do with tidal energy. Every moon that they've been able to detect and orbit on has been what's called tidally locked. means the moon always faces the planet that it orbits. So its axis of pull, the gravity that pulls on it, is always the same through the same part of the moon. Our own moon acts the same way. That's why we're always looking at the same face. But because orbits are elliptical, there's going to be a bigger gravity effect at one part of the orbit and a smaller gravity effect at another part of the orbit. What that does is as the moon gets closer on the right here to Jupiter in this case, the increased gravity will pull along that axis that's always facing the planet. As it gets far away, that force will be released. Never goes away, of course. But the result is every time there's an orbit, you get one cycle like an accordion player would run the handles of his instrument out and in. And that creates friction, and that friction is energy. Now, full disclosure, Jupiter has a high level of radiation this close in, so that adds a lot to the heat caused by the friction. But that doesn't change the fundamental conclusion of astronomers who are studying these moons. These are the Galilean moons, and you can see how short their orbital periods are. Io is the most volcanically active body in the solar system. Every 1.8 Earth days, it gets one big accordion cycle, and that creates a lot of heat. The rest of them, not so much, but it's enough to create a liquid ocean beneath the solid surface. The model we have right now is that there are rocky cores to these moons. There's enough heat generated because of tidal friction to create hydrothermal vents near the liquid water rock interface. And we're back to the geochemistry that I outlined earlier in the abiogenesis slide. Not saying that life is happening there, but all the ingredients would be there, and the heat would be there, and the circulation would be there. These products have been hot enough to make their way in liquid form up through 9 miles. I saw 9 to 15 miles. I'm still having a hard time buying that. So conservatively 9 miles of ice thickness on Europa and outgas into space. These are the chemicals that Cassini saw when it did its flybys of Europa. So what's in those vents, we'd very much like to know. Now, in no way can I claim that this is the same as the black smokers. But as I say, the conditions are similar. And of course, we have extremophiles that don't have any problem with that here on Earth. I think what they would be looking for here, though, are the substrates that we talked about again back in the geochemistry slide. And we're actually going to have a chance to do that. This is a funded, Europa Clipper is a funded probe. You can see it's supposed to launch in 2024 with a 6-year trek out to Europa to examine these kinds of chemicals in more detail. What about Titan, moon of Saturn? There's water here too. The atmosphere is 95% nitrogen, but it's just thick with organic compounds. It has methane clouds and it actually rains methane, so there's weather systems here. Has methane and ethane lakes, so there's surface liquid. Again, organic compounds, can they support combining into life forms? That's theoretically possible. There's additional energy. I put a question mark here. Cryovolcanoes with ammonia and water ice leaking their way to the surface. Put the question mark because they had the exact frequency and the exact constituents of cryovolcanoes doesn't sound like it's been totally confirmed. But there's enough activity here on the surface to change the topography. There are hills, there are dunes, and there are weather systems. This for a different reason maybe than Europa, is a prime target for life as well, or astrobiology. One thing to note here, though, is the atmospheric pressure is high, higher than it is on the Earth. There's only 14% the gravity. That is made for a flying vehicle. And sure enough, they have funded this for a 2027 launch. That's going to be a 9-year trek to get there. This is a flyer that is kind of necessary. You can't put a rover on the rough terrain, the varied terrain you see on Titan, but a flyer is ideal, and thick air and low temperatures and low gravity. This should be a very efficient flying machine. It's about as big as Perseverance or Curiosity, a little smaller, I think, like 7 feet high, 9 feet long, which makes Ingenuity about that high. I think I got my scales correct. But let's see. It's got 8 helicopter blades, and it can travel about 22 miles an hour. So it can cover a lot of ground at about 13,000 feet. And remember, this is a thick atmosphere. Ingenuity is arguably the more heroic application of aerodynamics. The surface pressure on Mars is somewhere akin to 150, 180,000 feet here on Earth. Very thin atmosphere that Ingenuity is operating in. I've been amazed it's done as well as it did. But we have 2 funded missions now, one going to an exomoon of Saturn, one going to an exomoon of Jupiter. Enceladus didn't make the cut. And most astronomers, for reasons I haven't been able to tease out, rank these things appropriately that way. They say Titan and Europa are better targets than Enceladus. I've always been intrigued by the tiger stripes, the large fissures that shoot out enormous geysers of organic material in the same way as Europa does. We won't know about that for a long time, but there was an intriguing result that came up this month. Some university did, I think it was in Britain, did a computer model of the chemicals that we see coming out of these vents and of the conditions of the ice and the heat of Enceladus itself. They say, okay, methane is part of that mix. Not a earth-shattering piece of news, but there's too much of it. It's producing more methane than a geochemistry process alone can account for. Does that mean there's life? I doubt it, but it's an intriguing result that chemistries are going on that we don't yet have, and organic chemistries are going on that we don't yet have a good handle on. Unfortunately, that's going to have to be a discovery for another day. Okay, that's kind of a wrap on what we're targeting in the next 10, 20 years for operations here in the solar system. Hopefully we'll answer some important questions with the Mars sample return. Moving into the galaxy, we're talking exoplanets. And these have been fairly recent discoveries. First was 1988, but it wasn't confirmed till much later. 1992, they found a couple of planets around a pulsar, and they discovered it because the pulsar timing was a little off. 1995 was the first discovery of I can't remember if it's an Earth-like planet or a planet around an Earth-like sun, but 1995 was getting closer to the kind of astrobiology that we're talking about here. As of July 1st, this is the number of confirmed exoplanets per the Planetary Habitability Lab in University of Puerto Rico. Since July, I reported at least 2 more, so even this number is a little out of date. But for astrobiology science, you want to find as many exoplanets as you can to see what the range and distribution of conditions are. How common are sun-like suns? How common are Earth-like planets? How many planets reside in a sun's habitability zone? The more data you have, the more accurate those numbers can be, and the more extrapolations, more accurate extrapolations you can make. There are 5 ways of finding these planets right now. I'm going to go through real quickly because I suspect everybody's already knows a lot of these things. Radial velocity is the frequency domain of the wobble of a star as its planets orbit it. This is appropriate particularly, I think there are maybe space telescopes that do it, but it's particularly effective for ground telescopes to do this kind of exploration. An exoplanet orbiting around, any 2 bodies orbiting will orbit around a common center of mass. So any exoplanet would shift a star's center of mass just slightly, and which means it's twisting off its spin axis. And that leads to a wobble. So sometimes the light, as that wobble is coming toward us, is raised in frequency. Sometimes it's lowered in frequency. But that's counted for about 800 exoplanet discoveries so far. It's a productive method. Okay, the transit technique is just looking at the drop in light level of a star as an exoplanet passes in front of it. This is accounting for 70% of all exoplanet discoveries so far. It's easy to interpret. It can be discovered at a number of different types of telescopes. TESS, the exoplanet satellite in orbit now, uses this pretty much exclusively. Direct imaging is cool for finding close-in planets. You take a coronagraph or something similar to blot out the sun, and you can see planets where that would normally be undetectable because of the light that a star is giving off. James Webb is one of many new telescopes, but it's the next big one that uses this technique, and it has its own onboard coronagraph. In the case of space probes now, these are all computer controlled. They're not just a flat disk like they used to be on some ground telescopes. But that's how James Webb proposes to do exoplanet discovery. Gravitational microlensing works as well. That's where a body with a lot of gravity, black hole, I don't know, neutron star, galaxy, will bend the light of a distant object around it, and therefore making that body along our line of sight visible. Now it creates a funky image that has, as you can see, it's splitting this one object into 2. They look funny, but they can be reconstructed, and they offer us a window into light patterns that we wouldn't see on our own. Well, we do that with stars. It turns out that that works just as well for planets. Star passes, you get another blip in the lensing, get another object in the ring. That's a way to discover exoplanets as well. I would have thought this was kind of an obscure or complicated way to do it, but it turns out 1 to 200 exoplanets have been discovered by this method. And the Nancy Grace Roman telescope is all about, her primary instrument is all about finding exoplanets with gravitational lensing. Finally, there's astrometry, which is basically finding an exoplanet's wobble, but doing it by direct measurement. In fact, this diagram looks better than the first one I had for radial velocity to show the effect of an exoplanet on the spin of its host star. Now, the data I had showed very few exoplanets discovered by this method. It requires very fine measurements. But since 2013, Gaia has been in orbit. This is a European Space Agency, European Space Observatory, ESO office. survey telescope, and it's collecting immense amounts of data. And they claim this is going to produce tens to hundreds of thousands of exoplanet discoveries in its lifetime. It's turned out 3 data sets so far. They're incredibly precise. I haven't seen the studies that have come out to say, oh yeah, we've got these new exoplanets or those new exoplanets. It may be that it takes longer to confirm them than I'm giving credit for, but they're making big claims. And so far what they've done by way of star surveys, I tend to believe that this would be a new measure, a new way of, a productive way of discovering exoplanets. Okay, you want a lot of them. Now, what do you do when you have them? You want to look for the ones that are habitable, and the topic here is astrobiology. Same 3 conditions apply to exoplanets, but now there are 2 additions. We know what our sun's all about, but there's a range of star types in our galaxy. And we know what our planet range looks like, our rocky planet range here in the solar system. But there are others that can assume drastically different sizes. So these 2 conditions are also considered when examining the habitability of exoplanets. The last one's easiest to deal with first. Some planets are so small that they don't have the gravity to hang on to either water or an atmosphere. So you want to rule out the real tiny ones. The chart that I have for this purpose says that's about 2% the size of the Earth. And I wasn't aware you could even worry about planets that small. But it is a constraint as part of surveying the galaxy. The star not too big or too small has to do with the habitability zone. There are 4 categories of stars that have habitable zones where liquid water could exist on the surface of a world. This graphic doesn't show F down at the bottom. G is our sun, K smaller, and then M would be like red dwarfs. You can see as the light and the energy drops, so does the size of the habitable zone, where enough energy can be transferred to a planetary disk to provide for water. But all these trends run in the same direction. Our sun has the class of stars, 10 billion year lifespan. The stars that are smaller, working up to M, have longer lifespans. That means they have more time for things to happen and things to stabilize. There are also more of them, a lot of red dwarfs. The downside, of course, is the radiance. As you get closer, X-ray radiation becomes more of a factor that can, to possibly sterilize what would otherwise be a perfectly good region for a planet with life to exist. So again, from Planetary Hab Lab, they claim there are 60 confirmed habitable exoplanets right now. This is their latest graphic. I don't know why they don't make one that consists of 60 planets. This doesn't. This is just representative. But that's all we have now. Hopefully there will be more as the Planet Finder space probes gather more data. Now, SETI has taken the data we have, and they've made these 2 statements. This comes out of their published materials. They do this for a living. Their statements are always carefully researched. I have no reason to doubt these. But again, I'm saying on the basis of 4,800 exoplanets discovered and only 60 of them found to be habitable. I don't know how stable these 2 numbers are. They may shift as we learn more about populations of exoplanets, but this is pretty optimistic as far as it goes. The primary tool for examining for biology on other exoplanets is measuring the spectrum of their atmospheres during a transit event. You take the spectrum of the star's light, you take the spectrum of the light that's passed through the atmosphere, and you work a subtraction on the changes. You're also looking for signs of disequilibrium. I have to think hard about what that means sometimes, but biology keeps any atmosphere, including ours, in a state of disequilibrium. Things are being brought in from the atmosphere, chemicals are being put back in, activities are causing changes in the location of and distribution of atmosphere, in addition to things like geophysical weather. So there are signals you can look for in the spectrum that would show you that, yeah, it looks like life is possibly going on here. But there are also some tricks you can run to polish up those kinds of estimates. One is to simulate the characteristics of Earth and its atmosphere, and in a computer, put it where an exoplanet is, the exoplanet you're studying. Say, well, if Earth were there, if that were Earth, what would it look like? And then examine the data you have to see the differences. It's a clever way of refining a spectrum, further finding, okay, well, we know we have life here, so what would it look like there? And do we see some of the same signs? It's something like what we see on a lot of Mars rovers. This is a calibration instrument that's put on Perseverance, but what it does is it gives color and contrast standards. Cameras can be put down and aimed at this. At the same time, it's imaging something else, and you can color correct. This is how we get our color corrected pictures of Mars. You can color correct based on the shifts that have occurred on this instrument. We're kind of doing the same thing here by putting a simulated Earth where an exoplanet that we're studying would be. Something else is to do a little astroecology. I already talked about one execution of that with Venus. Remember, they looked at phosphine. Okay, is phosphine there? Is phosphine not there? Where is it? Okay, the ecology comes in with the water analysis. Said, all right, biosignatures need to be considered within the environment that they're in. They interact with the environment. They're part of a context of materials. The water caution that was given for phosphine being evidence of life is an example of astroecology. Okay, what are those conditions there? Could life exist with the signals that we see based on known ranges of life here on Earth? And who knows, maybe we'll use Mars as a standard here in a few years when we know more about it. The other application is to do that in lab experiments and simply set up the conditions with particular kinds of materials and atmospheres and pressures and see if that exceeds the known ranges of organic chemical processes here on Earth. Is it hospitable? Is it impossible? So that's what ecology is all about. Now, there's one thing I'd add. I won't go too far with this. Last month, the Santa Fe Institute, which does a lot of exotic analytical work, published some results from a team that does mathematical biology. Now, what you see here is a nucleic acid formula. And we've all seen chemistry where the proportions of the elements are fixed for a particular molecule. And if they shift, it's a different molecule. But they tend to stay, I can't remember who the chemist was that discovered this. There's a law of constant proportions that goes from elements to molecules. Well, it turns out that you can make the same claim for the ratios of biomolecules themselves, and even up to types of life, the kinds of cells that are in your body. Life forms constant ratios that non-life does not. And the cool thing about this is it doesn't have to look like anything you recognize here on Earth. or for that matter, it doesn't have to be carbon-based life. If you're looking at constant ratios, you are looking at something that life has produced, something complex in a constant proportion. And if you can separate it from its surround, you can make that claim regardless of what it looks like. No one had, they brought up in the paper, they brought up the astrobiology implications of this, but I haven't seen it applied anywhere. It's way too soon for that. But it's just another way that you can take a spectrum, examine the constituents of an exoplanet or its atmosphere, and make statements, all of these tools, and make statements about how likely life is to exist there. Okay, what about exomoons? Exomoons are, yes, they're out there. We've discovered them, I think mostly in Kepler data. The only thing I'll say is, again, in July, they've discovered 4 possible Earth-like rogue exoplanets in Kepler data. The reason an rogue exoplanet is one that doesn't have a sun. It's not orbiting anything, but it could still have moons, and that's why astrobiologists are interested in studying rogue exoplanets should they ever build up a big enough database. Okay, so why haven't we found anything? The first exoplanet atmosphere wasn't observed till 2001. It's still early. And as you can see, the signals are exciting, but they're still ambiguous. We're confining ourselves to Earth-like chemistries right now. That's probably wise. The best searches are done with smaller stars because you can look at rocky planets closer to them. And the best telescopes, as I've shown you already, I'll show you a couple more in a minute, won't be online for the next 10 or 20 years. So the data are about to come in, but we're gonna have to wait for them. These are just briefly examples of that. The extremely large telescope claims to be able to look not just at atmospheres, but at surface spectra for exoplanets. That'll be interesting. Louvois is not going to launch for like 20 years. It's looking for exoplanets in all 3 major bands, ultraviolet, optical, and infrared. Now it has a complex coronagraph. I wanted just to show HABEX here, which is technologically just as far along, no scheduled launch date, but it has what they call a star shade. They're going to move that up to 47,000 miles away and orbit it and let it do its thing of blocking out solar light that way. Okay, quick run around for technosignatures. The cool thing about technosignatures is if you see evidence of an intelligent life in the universe, you solve the biology question at the same time. You get a twofer there. Unfortunately, this is going to have to all be passive, looking at communications and with technological artifacts. This is Tabby star. You might remember, they still don't know what's causing it, but the light dimmed and they thought it might have been some kind of a superstructure around the star to harvest its light by an advanced civilization. The 2 groups doing communication study are Breakthrough Listen and SETI, both of them privately funded, started looking at the radio spectrum in the 70s, primarily around the 21 centimeter hydrogen line, because we thought any intelligent species would know that we looked there. It's a common element. Since then, they've expanded that to infrared and laser. I think, Ken, you mentioned something like that for Palomar. So they recognize that there are different forms of communication we couldn't restrict. Most recently, I've seen talk about quantum communications, which is entangling qubits. They make it sound like it's not a problem. I don't understand how quantum communications work such that we would accept signals from a civilization that wasn't directly beaming them to us. But apparently that's totally possible. Looking for artifacts, in this case, atmospheric disequilibrium. Optical and radio telescopes can do this. The best example I can give you in this case that they talk about is smog and industrial pollutants. This is a particular kind of life product that would indicate a technological life. Now, recently, SETI and Breakthrough Listen have got a proposal funded at NASA that they're going to use their equipment to look for exocomets. But they also wrote into it, oh, by the way, if we discover any megastructures, we'll be sure and let you know. So it's a way of piggybacking a technology search onto a straight astronomy search, which I thought was pretty clever. That work is just starting up. The ultimate techno signature, of course, you've seen the reports, as have I. There are people who are skeptical about that, but no one can disprove it. Seth Shostak is a senior astronomer at SETI. He said if they're going to send anything this way, they're not going to be aliens and spaceships. They'll send technology. So if there's something here, it's autonomous, it's mechanic, technological. This is Avi Loeb. He's at the Harvard University, a senior, well-respected astronomer. He's been real aggressive lately in thinking that aliens are here. We should welcome them. We should be much more open into how we interpret the data. He even proposed that Oumuamua might have been a probe. He's been criticized by the community for that. The magazines he publishes in have been criticized by journalists for putting it in, but he stands by it, and he is a serious, sober astronomer. So that's kind of where that stands today. Last slide is recently, both this month, 2 studies in July, turned the observation of exoplanets on its head and said how many stars could see us with the transit method. And with drifting stars within plus or minus 5,000 light years, they found there's like 2,000 of them. Another one found that 7 star systems are within 100 light years, contain 29 habitable planets, which is a goodly number to be so close. Those 2 studies are completely independent, though. It'd be nice to see who can see us, who's in range to have received our inadvertent radio signals and maybe be in a position to respond, and can identify us from and study us from transit, but that hasn't happened yet. Okay, 3 approaches to this, which are embedded in everything I've talked about. And the principle of mediocrity is kind of unfortunately named, but it says we're not special. It's been around for a long time. There's a good statistical logic behind it. Carl Sagan believed in this. I think most astrobiologists dare buy into it. It says we're typical. We are probably typical of the universe. We have no reason to believe we're special. Contrast that with the rare Earth hypothesis, which is we are special. Life may have form, but it's not intelligent. And that leads to the most pessimistic, which is the Fermi paradox. Said we are a young solar system in the history of the universe. Why haven't we seen older civilizations doing space travel by now? So they must not be there. There are a lot of cogent arguments against that. But until we find something, that's the way it's going to have to stand. Finally, I just stumbled on this morning. If anybody's interested in this, this is the golden standard for SETI. She's going to give a talk tomorrow night as part of the Summer Symposium series, Astronomical Society of the Pacific. And there's the website if you want to go look it up. I know I'm going to tune in. With that, I'll take questions. I think I need to give the screen back.
I have a question. Can you hear me?
Sure.
Hi, it's Jeannie. I have a little story. It was 1971. I was just starting as an undergraduate at the University of Maryland, majoring in astronomy, but they didn't have a work study program in astronomy. So they sent me over to see a chemist and to work for the chemist. So my interview was with Dr. Panam Paruma. And through the interview, he mentions the Murchison meteorite, which he had discovered amino acids in. Do you know about it? And I said, oh, yes, I read about it in Sky and Telescope. So I did get the job and got to work for Dr. Panam Paruma in the Laboratory of Chemical Evolution for 2 years. I actually got to meet Harold Urey. His friend came out. We did the Harold Urey, the Miller-Urey experiment. We built our own flask and did that and had many results. But back to the Murchison, it gave us racemic mixtures of amino acids, meaning right-handed uh, and left-handed. We are left-handed creatures, but the right-handed just as much. So that was great. And the last thing I did over there was clean a room just to the nth degree, getting ready for the moon rocks. He was getting moon rocks to analyze. So it really resonated with your story. So to this very day, I'm fascinated by exoplanets. I tell young people about them 50 years later, and I have the Exoplanet app on my phone. And I can tell you when I wake up in the morning and it says, we just discovered this many more exoplanets, I am tickled pink. And this is just such an awesome time. I can't wait till the Webb telescope goes up and does analysis of the atmospheres and looks for that dynamic change. So yeah, so I did run across oh, I've met Jill Tarter. Yes, she came to San Diego to the uh, she's fascinating. So I look forward to her lecture. And I met Arthur C. Clarke as well. So
Oh, that's cool.
yeah, so that was when I was a youngin, 50 years ago. Yeah,
That's a cool story. Quick question. You mentioned left-handed. You're talking about chirality?
it's of the racemic mixture of amino acids. If they're made organically, they're left-handed. Inorganic are right-handed. And to get the ratio to be both, to be 1 to 1, I think that's it. They're made inorganically. Whereas if you analyzed, something on Earth, that would be most all left-handed because of the way we play chemistry here. That's as much as I know.
No, thank you. I'm glad you explained that. I wasn't sure I could. I have read about that as part of biosignatures as to what's likely of extraterrestrial origin here and what's maybe closer to home. But I didn't think I could explain it clearly. So thanks for what you just gave.
Well, thank you for a fascinating lecture and beautiful slides and visions of the future. There's just so much to look forward to out there. And Perseverance only landed on this year on February 18th. Why do I know? Because my little turtles hatched on February 18th, Marty and Percy. Marty and Percy hatched the same day. They're like little rovers.
Oh, yeah.
I know. Thank you very, very much.
Thanks for the story. Ken, while I look, I called up the chat and I don't know who AC is. I don't see him on, but he listened to the presentation. And I don't know if you've seen for everybody, he said, technically lipids do not contain the carbon, double oxygen, hydrogen. This is a fatty acid that's shown. So I knew I'd slip up somewhere, and apparently that's what I cut and pasted. The formula is wrong there. He also said a vegetation red edge biosignature on exoplanets would be a more direct evidence of photosynthetic life as a spectroscopic observation. I'm absolutely certain I haven't surveyed every single tool that's used, but he made that comment. I'll certainly take a look at it. I'm interested now too.
Let me ask a question about the timeline. Going from the possibility of creating amino acids through the process that has been verified experimentally to, and we've all seen diagrams of one cell life, multiple cells, some kind of whole progression that's guided by natural selection that ultimately gets you to something that walks out of the water. Is this all theoretical, or is there any evidence, either current or fossilized, of that progression of life?
I'm speaking personally here now. we're having trouble finding links in the evolution of hominids,
Yeah.
which go back 2 million years. There are periodic windows. I'm totally blanking now. The structures in Australia, what did I call them? I've just lost it. Pre-oxygen cyanobacteria. There are, say that again?
Stromatolites.
Yeah, I just totally lost it there.
Okay.
But so you get periods that are like that to say, this is what it looked like at this time. Cyanobacteria, I think, are what they call protokaryotes. They don't have a defined nucleus with a membrane. There are cells that don't look like any kind of cells today. The cells themselves had to evolve. How fast that was, I don't think anyone's going to draw a good straight line there other than theoretically, because the Earth has changed so much. A lot of the materials aren't on the surface. A lot of the deep materials are now on the surface. You saw the pictures of volcanic activity. We've had a couple of ice ball planet episodes. So it doesn't surprise me that they can't draw $4 billion, 4 billion light year timeline like that. But they do have snapshots, and I think the first one is I think the 3.8 billion year light year, 3 billion year figure that I gave, where they think they have examples of microbes. I'm sure they look a lot different than anything we would find today. I hope I didn't dance around the question. I think the answer is no, but it's almost I can't imagine how they would ever get yes.
Yeah. Well, when I heard about that, the visible and infrared SETI program, all I could think of, and I'm still wrapping my head around that, more or less from a power budget standpoint, is like, well, if we get a magnitude 20 star, and I guess Palomar theoretically, although it depends on how you calculate it and what technology you're using, can probably get a magnitude 23 or 24. But nonetheless, that light that we detect with the giant telescope came from basically a fusion reaction, and that's just the light. Now, if you tried to modulate the light in some kind of communication or beacon or something like that, light is kind of tough. Then you either have to modulate the power source or you have to put a shutter, which is totally impractical. So I can't quite understand how we'd expect to get visible light sources from a civilization on some other planet.
I'm certainly don't want to come across as defending that. I think the logic there, and I'm speaking for people who know way more, they do it for a living, is that's a technosignature you're talking about, right?
Yes, I think so.
Yeah, so the onus would be on the civilization sending the signal. It's kind of like not our problem. If you want us to speak or to hear you, it's up to you to use whatever technology you have to make that happen. It kind of relieves us of any obligation to come up with our own technology as an example for such a civilization. Does that make sense?
That makes sense. But of course, we haven't elected to do that. Some sort of a giant signaling device that would be aimed at some of the several thousand planets that could conceivably see us. I'm just having trouble working out why anybody would invest on such a system so that they could be detected by another life form.
You touch on a really sensitive issue. I had thought, I don't want to say I snickered, but I discounted people who said that we should not send out signals. There is a camp that says it's dangerous. You don't know what you're getting into. Why are you announcing your presence? It's like a deer shouting in a forest with tigers all around, and not a good idea. that used to not be taken seriously, but there are enough smart people that do take that seriously these days to give pause. So to answer your question, why would they do it or why would we do it even if we could? That's a different debate, but it's a very serious one. People may not be communicating for exactly those reasons. Nobody knows what's out there. Nobody knows who's going to answer.
I have
More?
a question.
Go ahead.
Can you do, Steve, thank you for the lecture. It's very interesting. Can you define in more detail the difference between gravitational lensing and microgravitational lensing, please?
Not in any coherent way. I don't know if I used the terms correctly, but the idea is that light along a line of sight passing around an object with very high gravity will have that light bent to either side and back again. So you see the object that normally would be a bit invisible to you. You see it spread out to the side of the lensing object. And of course, you have to reassemble that into a coherent image. But the idea of gravitational lensing and micro lensing, I think, is one of scale. I'm afraid that's all I know.
I thought there was more of a difference, like was way smaller objects, or I don't know. I pretty much
You may very well be right.
I just didn't know what micro gravitational lensing is. Yeah.
I think you're correct from the physical diagrams I've seen, depictions of that. Micro lensing may be with smaller bodies. I mean, anything with gravity is going to bend light. Depends on how far the object is you're looking for, how far away, well, I guess at those distances, it doesn't matter. But I would imagine it's just one of scale. I have seen smaller things used as examples of micro lensing. I just don't know enough to give you something clear between the two terms.
Just, I stumbled on something when I asked the previous question, and it really was, assuming we wanted to develop a communication system and radiate energy and say we're here, which, as you pointed out, that is still a debatable point. But it would be a significant investment. So with some limitations on our science and technology budget, if we do that, we don't do other things. Do you have any rough order of magnitude of how much, SETI-like experiments represent as part of our total, say astronomy budget or science and technology budget? Are we looking that hard?
I talked to Seth Shostak on that, the astronomer at SETI. The answer for taxpayers is effectively zero. These things are privately funded. Yuri Milner bankrolls, Breakthrough Listen. Whatever that budget is, it makes SETI kind of envious. So I would imagine SETI's is less than that. But other than the kind of specific project funding I just mentioned for exocomets, it's all coming from various sources. I know you can donate to those people. It's not a big budget at all. Converse, and most of the people that work there seem to have university affiliations, which is probably where most of their salaries come from. But in terms of coming up with a system to transmit, I'm not aware of anything like that going on, and I wasn't aware, talking to Seth, because he is aware of the debate of should we transmit or not at all. I wasn't aware of anyone anxious to do that. If we had a signal, that might change overnight, but we've had nothing so far. So why set up a transmitter? And if you did, who would you aim it at, and why would you aim it at them if you didn't know anybody was there?
Yeah, that's always a rough feasibility thing, and the two societies have to be at some relative coherent level of technology. You know, if we're in the nuclear age and they're at, you know, back in the sailing ships, they'll never hear us.
Well, this is armchairing on my part, and I don't want to go too far with it, but I mean, anthropologists make contact with remote people all the time. Certainly the last century's been rife with that. And for all the bad things that have happened as a consequence, I think you can usually develop some kind of a protocol for a society that doesn't have the tools you do. If a society wanted to contact us, I don't think that would be an issue. I'm speaking just on the reading I've done, though. I have no special expertise there. This idea that they'll be so advanced, they won't want to have anything to do with us, or they'll just destroy us. I think that's a little simplistic. But if they wanted to contact us, I think they could do it. Which you know, begs the question, then why aren't we seeing anything?
Well, one thing we should note is that our planet has been signaling out for almost over 100 years now, and radio waves and such. And they may have seen our issues on television of Gilligan's Island and didn't want to talk to us.
Yeah. I've heard that joke before, but yeah, there may be a good reason why they're not messing with us.
But on the serious side, we have been transmitting significant signals for the past 100 years.
Yeah.
Someone's going to hear us if they're out there.
Just an aside, this presentation went on kind of longer than I'd expected to begin with, but I had a slide that showed 17 habitable exoplanets within 40 years of us. The nearest one, Proxima Centauri, was only 4.5. So as you said, if we started sending transmissions about a century ago, signals that could be picked up, that's plenty of time to receive it, think about it, understand it, and decide whether or not to respond. If there are intelligences out there, they're either not there, or they're there and for various reasons have missed us, or they see us and they just decided not worth the trouble. I don't know how that's way down the road for what astrobiology is probably dealing with these days. Yeah, there are signals and there are habitable planets that would have received that by now. So what follows, I can't predict.
Thank you.
I'm reminded of the Drake equation, and he was, Professor Drake was at the University of Maryland as well when I was working there. So there's
fantastic man, and I've heard they've been able to whittle down some of the terms of that equation significantly as a result of this kind of work, especially the exoplanet search. But there's still a lot of wiggle room in that one.
Steve, I have a question for you. Have you heard any talk or speak or mention of difference in the habitable zones of binary star systems, and if there's greater potential or any change in potential for the habitable zone of binary systems?
It's funny you mentioned that. San Diego State University has a pair of astronomers that have done a lot of work, I think with Kepler data, or even Spitzer, but I think Kepler, with planets orbiting binary star systems. They're more common than I ever would have imagined. I haven't seen anything on whether those represent habitable zones or not. I mean, it's inherently unstable. You go around one star and then another, and then they're in line, and now they're side to side. So the environmental conditions ought to change significantly, but that's all I can think of. The experts are here locally, though. I thought that was kind of neat. We had them speak about 1.5 years ago, I think, at one of our meetings.
Yeah, I worked with Pat Boyce and for his double star system, and so that was one of the things that came up that I proposed. And I didn't know it had any weight to it, but I thought it was a fascinating question as well. Do you know either of those astronomers' names by chance?
No, I'm sorry. If you Google San Diego State University binary stars, I'll bet you a paycheck that they'll turn up those names. Ken had them on our speaker list. This was before the pandemic, but one of them came out and talked to us about exactly that topic.
Bill Welsh is one of them.
Perfect. Thank you, everybody.
Yeah, great.
Yeah, he's one of them. I can't think of the other.
Jerry Oroz, Dr. Oroz.
Jerry Rose, yes.
Yeah,
There you
yeah,
go.
the other one.
Name rings a bell.
Those are great guys.
Steve, you've just given us a fabulous talk and we've kept you for a very long time. Are there any last questions? No? Well, then let me conclude the meeting. And again, thank you so much for the great talk and very thought-provoking. The next month, we are going to have a talk from the principal science investigator at JPL for the Near Earth Asteroid Scout mission, which is a CubeSat. And it has some very interesting design features, but she will cover basically the history of searching for near-Earth asteroids with pan-stars and ground-based astronomy, as well as the space missions. So that should be interesting and tie into our own Jerry Hilburn's work at the ASIG group, where he has been teaching us how to actually image these things and get little star trails or little asteroid trails on our own. So with that, let me conclude the meeting. Thank you all for coming. Hope to see you next week. And please start coming to the star parties that we're finally being able to schedule. Thank you. Good night.